Welcome back. In this lecture, we will look at the dynamics of a nuclear fission reactor. This is a follow-up on the previous lecture where we had derived an expression for effective multiplication factor in a nuclear chain reaction. So this depends on a variety of factors as was mentioned in the previous lecture. So please go through the previous lecture to understand the implications of K effective. We can define something called the lifetime or the generation time. This depends upon the nature of neutrons that are present. It can be delayed neutrons, unprompt neutrons. All these things have to be taken into account to define this tau. So that is related to the generation. So if you remember, when we had started our discussion on nuclear decay, when we defined the half-life, we had defined something like the first generation. And when another T half is done, we had the next generation and so on. In a way, the concept of generation time is related to that. But when you consider the process in a nuclear reactor, this definition of tau becomes more complicated. It is not a simple T half. But the notion of generation time and generation has connections to our simpler system of just you have one radioactive decay, and with every generation, some T half has been taken into account. That is, the concentration or the population decreases by half for every T half. So here, what we are going to consider is if there are n neutrons after generation m, if one more generation passes, that is, you've gone to m plus 1 generation, the effective amount of neutrons you have is n times K effective. So if you remember, this is the multiplication constant. This has to be greater than 1 if you want to sustain the chain reaction. If it is less than 1, you are having less neutrons than what you are using up. If K effective is more than 1, you are generating more neutrons than what you are using. So n times K effective is the amount of neutrons available after m plus 1 generation. So the change in the number of neutron between m to m plus 1 generation can be obtained by simple subtraction. You get this. So this change occurs in this time, right? So dn by dt can be written in this manner. You can simplify this as K excess. Why do you use this terminology? Because we want to have more neutrons than what you're using in a nuclear reaction. That is, we had seen for many fuels, let's say around 2.42 neutrons are generated when U-235 undergoes fission. But all of this is not utilized only for fission. Some of this gets dissipated in some other manner. So K excess is indicative of how many more neutrons you have beyond what is being used. One is being used, and this is the amount you have more than what is being used. So that's why we have this terminology. This is the effective multiplication constant. This is the excess multiplication constant. So once you have this differential equation, this is the differential equation for figuring out how neutron changes, the number of neutron changes with respect to time. If you integrate, you get a simple equation. Um, but you should remember these factors are dependent on the configuration inside the nuclear reactor. It is not just a property of a single reaction, but more to do with many other factors. So this is typically obtained either via experiments or via simulations. So all these factors, that is k exists by tau, can be combined into this. This is called the reactor time period. This is the time. So it is also important to note that when you're when you're having tau, it has to do with both the prompt and delayed neutrons. Unless you take both into account, your description is not complete. In the next lecture, we will go into the different components of a nuclear fission reactor. Thank you.